Hello everyone. Today we will focus on sound waves, which come about through mechanical waves traveling through air that result in the human sense, hearing. The way and range we can hear of waves. There are three categories of waves: audible waves, infrasonic, and ultrasonic. The way we hear. Elements of air are disturbed from their equilibrium positions, which causes change in density and pressure of air along the given direction of motion of waves, causing what we are able to hear, sound. Audible waves exist in range of existence to the human ear. Infrasonic frequencies below audible range. Ultrasonic frequencies above audible range. Here are three examples of some sound waves that we can hear and/or how other animals can hear. For audible waves, we are able to hear musical instruments. Infrasonic, for whales, they communicate with each other through infrasonic waves underwater. And ultrasonic, dog whistle is how to grab a dog's attention, although we can't hear it. Also medical imaging. Pressure variations in sound waves. As we look to the left in figure 17.1, we could see that a one-dimensional periodic sound waves can be produced in a tube of gas by a piston moving in simple harmonic motion. The darker parts represent where gas is compressed, and the density and pressure are also above their equilibrium values. The compressed regions are formed whenever the piston is pushed in the tube. Rarefactions are the inverse of compressed regions, in which these parts have lower pressure. Both move at the speed of sound. Defining compression and rarefactions. Distance between two successive compressions or two successive rarefactions equal the wavelength of a sound wave. This can be mathematically explained as x of x and t, which is the position of a small element, relative to its equilibrium position, x of x and t, S max cosine kx minus omega t, referred to in equation 17.1, where S max is the maximum position of the element relative to equilibrium, which is usually called the displacement amplitude. Variation in gas pressure, delta P, measured from the equilibrium value, is also periodic with the same wave number and angular frequency as for the displacement in the previous equation. Delta P is equal to delta P max sine kx minus omega t, where the pressure amplitude, delta P max, is the max change in pressure from the equilibrium value. And volume, in terms of compression and rarefaction, is equal to initial volume is equal to area times the change in position. Defining pressure variation mathematically. Looking back into previous classes about the bulk modulus in chapter 12, we can express pressure variation and substitute with the S of x and t when altering the formula to delta P is equal to negative b times the partial derivative of S over x, which S is x and t. From that we get negative b times the partial derivative over x times S max cosine kx minus omega t is equal to bs max k sine kx minus omega t, resulting in the final equation when simplified to delta P is equal to b S max times k, which shows that the relationship depends on the bulk modulus of the gas, which is not as readily available as is the density of the gas. To sum this up, pressure variation is a maximum when displacement from equilibrium equals 0, and displacement from equilibrium is a max when pressure variation is equal to 0. Speed of sound waves. Referring to the right at figure 17.5, we see an undisturbed gas in a non-isolated system, which exhibits a change in momentum where after some derivations with some equations will give us how to calculate the speed of sound change in momentum to the intensity, which I shows the sum of forces multiplied by a change in time is equal to area times the change in pressure times the change in time in the I hat direction, which becomes intensity is equal to A times B multiplied by Vx over velocity times the change in time in the I hat direction. And then after substituting and a little manipulation around, we receive the speed of sound in gases with a general form shown as velocity is equal to the bulk modulus over density under the square root, where the speed of all mechanical waves follow the general form velocity is equal to the elastic property and inertial property under the square root under given circumstances. Although speed of sound also depends on the temperature of a medium, in which can be defined with the formula velocity is equal to 331 times the square root of 1 plus the dependent temperature divided by 273, which is room temperature in kelvins. Power of periodic sound waves. Consider a simple harmonic motion in a sense where a piston is oscillating while acting on a gas at an angular frequency omega, where a length becomes so small it is negligent, where now the element moves with constant velocity. Then we could define power as the piston is doing work at any time, in which power is defined as force vector multiplied by velocity in the x direction, resulting in power equaling density multiplied by velocity times omega squared times area times sine squared kx minus omega t. And with that, we can get the average power equaling to half of density times velocity multiplied by omega squared and area and S max squared. Intensity of periodic sound waves can be described as the power per unit area as the rate at which energy transported by the wave transfers through a unit area perpendicular to the direction of travel of the wave. Intensity is identical to the average power over area, and the three parts that encompasses the figure to the right are the spherical wave, which is the whole figure, the wave fronts, which are the three arcs, and the rays, which are the 5 lines going outwards from the source. The Doppler effect. The simple meaning is what you hear as a vehicle approaches you is always a higher frequency than after the vehicle moves away from you. An example of this is when the pitch of an ambulance siren while passing by and the shift in red light is an example of the Doppler effect. There are 4 mathematical formulas which depend on the circumstances, although all 4 depend on the observer and the source of where the sound is coming from, and they can all be summed up into one formula. Shock waves. I personally am always fascinated about these while at the airport, and the fact I can hear them right outside my house. You can hear the sonic boom from the jets, and you could hear a sonic boom from a bullet, and you could also hear a sonic boom from lightning, which is called thunder. And shock waves are an occurrence when speed exceeds the speed of sound, which causes that explosion noise. Thank you all for being here for my presentation. Here's a recap of what we learned. How we can hear and the ranges of sound waves. 3 categories of sound waves: pressure variations, compression and rarefaction, speed of sound, power of sound waves, intensity of sound waves periodically, the Doppler effect, and shock waves. Thank you. I hope you all have a nice day.